right now sitting in sealed containers in laboratories in Beijing. There are grains of moon dust that contain something scientists spent half a century insisting could not exist there. Not buried in shadow, not hidden at the poles, but sitting in soil that gets blasted by direct sunlight for 2 straight weeks at a time, water locked inside crystals, surviving conditions that should have boiled it away billions of years ago, for most of the modern space age. The story of the moon was considered settled. It was a dead world, a dry world, a place where the internal furnace shut off billions of years in the past and nothing interesting has happened since. That version of the moon came from real data collected by real missions, and for a long time it was the best answer anyone had. It just turned out to be incomplete in ways nobody expected. The samples brought home during the Apollo missions and the robotic Soviet lunar missions shaped almost everything we thought we knew about our nearest neighbor. Geologists built entire theories of lunar formation, lunar cooling, and lunar chemistry around that material. It was treated as ground truth for generations. And within that ground truth, the moon looked like a fossil, a frozen artifact of the early solar system, useful for studying the deep past, but with no ongoing story of its own. That picture has now been dismantled, piece by piece, by a research program that most people outside planetary science barely paid attention to until recently. China's lunar exploration effort, built around a series of missions named after the moon goddess Chang'e, has spent the past 2 decades quietly assembling the tools, the technology, and eventually the fresh samples needed to challenge almost everything the old consensus assumed. The list of what has changed is not small. Scientists have identified stable water crystals sitting in full sunlight, something considered physically impossible under the old models. They have found naturally occurring graphene and graphite structures in soil that was supposed to be nearly free of carbon. They have dated volcanic rock from the far side of the moon to an age nearly 1 billion years younger than anyone predicted. Magma could still exist there, and they have catalogued a growing list of chemical resources, including a mineral that may double as both a water source and a nitrogen source, plus a rare fusion fuel isotope embedded directly into the regolith. Individually, these are interesting footnotes. Together, they represent something much larger. They take the moon from being a museum exhibit, a static rock we study for clues about the ancient past, and turn it into a live geological system with a resource inventory that could support a long-term human presence. To understand how we got here and why these findings matter as much as they do, we need to walk through the entire arc of the program that produced them, a 4-decade gap in lunar sampling, a careful 3-phase engineering strategy to close that gap, and the specific discoveries that came pouring out once fresh material was finally back on Earth. The story starts with silence. For 44 years, nobody brought home a new sample of lunar material. The last mission to do it was the Soviet Union's Lunar 24 probe in 1976, which returned with roughly 170 grams of soil. After that flight, the return missions simply stopped. Apollo had already ended a few years earlier. The robotic Soviet program wound down not long after, and for the next several decades, the entire discipline of lunar geochemistry had to work with whatever had already been brought home. This was a serious limitation, and scientists at the time understood it was a limitation. All of the physical samples collected during the Apollo and lunar programs came from a narrow band of the moon. The landing sites were clustered close to the equator, and every single one of them was on the near side, the hemisphere that permanently faces Earth. Nothing was sampled from the poles. Nothing was sampled from the far side. Nothing was sampled from many of the geologically distinct regions identified through orbital imaging in later decades. Think of it this way. Imagine trying to describe the entire geology of planet Earth using only soil samples collected from a single desert basin. You might learn a great deal about that specific desert, but you would have no basis for saying anything reliable about rainforests, mountain ranges, ocean floors, or polar ice sheets. That is roughly the situation lunar science was in for nearly half a century. A detailed, scientifically rigorous understanding of a very small, non-representative slice of an entire world, mistaken for a complete picture of the whole. Scientists were aware of the bias. Orbital missions using spectrometers and radar had already hinted that other regions of the moon looked chemically and geologically different from the Apollo landing zones. But hints from orbit are not a substitute for material you can put under an electron microscope. Without new samples, the old models simply could not be tested, let alone corrected, so they persisted, not because anyone believed they were the final word, but because there was no fresh evidence available to challenge them. That is, the vacuum the Chinese lunar program was built to fill. And critically, it was not approached as a single dramatic mission. It was designed as a staged 20-year engineering campaign, often summarized with a simple 3-word roadmap: orbit, land, and return. Each phase built the technological foundation for the next, and each phase produced its own scientific payoff along the way. The first phase was purely observational. 2 orbiter missions, launched in 2007 and 2010, were tasked with mapping the lunar surface at high resolution. Their job was not to touch the ground, but to build the most detailed 3-dimensional terrain models available at the time. Those maps did something quietly essential. They let mission planners identify safe landing zones in regions that earlier exploration eras had never surveyed closely enough to consider. You cannot land safely on ground you have not properly mapped, and for decades, most of the moon fell into that category. The second phase moved from observing the surface to touching it. In 2013, a lander delivered a small rover to the surface, testing the technology needed to survive the brutal swings of the lunar day and night cycle and to communicate reliably across the vacuum back to Earth. That mission alone would have been a meaningful achievement, but the follow-up mission pushed further, attempting something no country had managed before: a soft landing on the far side of the moon. Inside the volcanic crater, landing on the far side sounds like a simple extension of landing on the near side. But it is a fundamentally different engineering problem, one tied directly to the reason the far side had never been sampled before. The moon is tidally locked to Earth. Its rotation period and its orbital period around Earth are identical, which means the same hemisphere always faces us and the opposite hemisphere never does. A spacecraft on the far side loses direct line-of-sight radio contact with Earth the moment it passes over the lunar horizon. The rock of the moon itself blocks any signal attempting a direct path to solve this. Engineers placed a relay satellite in a specialized halo orbit beyond the moon, positioned so it could see both the far side lander and Earth's ground stations at the same time. It functioned like a mirror hung in space, bouncing commands out to the lander and data back to mission control. Without that relay infrastructure, a far-side landing, let alone a far-side sample return, would have been operationally impossible. This single piece of infrastructure is one of the quieter but more important achievements of the entire program, because everything that followed on the far side depended on it. That far-side lander mission also carried out a small but symbolically significant experiment, a sealed mini biosphere containing cotton seeds, which briefly germinated on the lunar surface before the extreme cold of the lunar night ended the experiment. It marked the first time a plant had ever sprouted on the moon, even briefly, and it demonstrated that biological experiments were viable within the harsh constraints of lunar missions. With the orbital mapping complete, and the landing and roving technology proven on both hemispheres, the program moved into its third and most demanding phase, sample return. This is where the real scientific payoff was always going to come from, because there are limits to what a robotic rover can determine on site. Identifying specific hydrated minerals, mapping carbon structures at the atomic scale, or precisely dating volcanic rock through radiometric analysis requires laboratory equipment, mass spectrometers, electron microscopes, that simply cannot be miniaturized and shipped to the lunar surface. You need the actual material back on Earth. The mission that finally broke the 44-year drought launched in 2020, targeting a broad volcanic plain known as Oceanus, an area that orbital imaging suggested was geologically younger than any of the sites Apollo or Luna had ever sampled. The mission succeeded, and it returned just under 2 kilograms of fresh lunar material. For the first time in nearly half a century, researchers with modern instrumentation had something entirely new to study, and they had specifically chosen a region that promised to be different from everything sampled before. What came out of that material, once teams of geochemists actually got their instruments on it, is where this story stops being background and starts becoming genuinely strange. One of the earliest results to come out of the new samples, announced in 2023, concerned something that is not rare or exotic at all. If you look closely at lunar soil under magnification, a large fraction of it is not made of jagged rock fragments the way you might expect. A significant portion consists of tiny glass spheres, some smaller than a grain of sand, scattered throughout the regolith. These are called impact glass beads, and researchers have known about them since the very first Apollo samples came home. They form through a violent but simple process. The moon has no meaningful atmosphere to burn up incoming debris, so micrometeoroids strike the surface directly, often at extremely high velocities. Each impact generates an intense, localized flash of heat, hot enough to instantly melt the surrounding dust. That molten material is thrown up into the vacuum, and because there is no air resistance to slow the process, it cools and solidifies hardening into a nearly perfect microscopic sphere before falling back to the surface. Multiply this process across billions of years and countless impacts, and you get a soil that is riddled with these tiny glass beads. What changed in 2023 was not the discovery of the beads themselves, but a new understanding of what they were doing chemically. Researchers turned their attention to how these beads interact with the solar wind, the constant stream of charged particles, mostly protons or hydrogen nuclei, that the sun continuously emits in every direction on Earth. Our planet's magnetic field deflects the vast majority of this radiation before it reaches the surface. The moon has no comparable magnetic shield. Its surface takes the full, unfiltered exposure day after day. For billions of years, the glass beads, it turns out, are chemically well suited to interact with that hydrogen. They are rich in oxygen because they are made from silicate minerals, and when high-energy hydrogen ions strike the glass, they penetrate the outer surface and can bond with oxygen already present in the structure. This is a process called ion implantation, And the result of that bonding is the formation of water and hydroxyl molecules directly inside the glass itself. This is not liquid water in any conventional sense. It is chemically bound water, locked into the internal structure of a microscopic bead, formed molecule by molecule over immense stretches of time through steady solar wind bombardment. The truly significant part of this finding is not simply that the water exists, but that it is not permanently trapped. The analysis showed these beads are part of an active exchange process. As temperatures shift across the lunar day and night cycle, or as beads become saturated with hydrogen, they can release some of that stored water back into the moon's thin, transient exosphere. This solved a puzzle that had bothered lunar scientists for years. Instruments in orbit had already detected water molecules moving around the surface during the lunar day, appearing and disappearing in ways that did not match any obvious surface reservoir. The reservoir, it now appears, is the soil itself, functioning almost like a planet-wide sponge that absorbs solar wind hydrogen and slowly redistributes it as conditions change. The scale of this reservoir is difficult to overstate. Based on the concentration of these glass beads found in the returned samples, researchers estimated that the upper layer of soil across the entire lunar surface could be holding somewhere in the range of 270 billion tons of water, distributed as chemically bound molecules inside countless microscopic glass spheres. That number reframes the entire conversation around lunar water extraction. Previous strategies for future lunar bases assumed that meaningful water reserves would only be found as solid ice, hidden inside permanently shadowed craters near the poles, regions so cold and dark that any exposed water ice would never sublimate away. Mining that ice would mean operating in near total darkness at extremely low temperatures, in some of the most inaccessible terrain on the moon. This discovery suggests an alternative that could be far less logistically punishing. If the water is chemically bound inside glass beads distributed across ordinary sunlit soil, then in principle a future outpost would not need to trek into permanent shadow at all. It could process regolith collected right next to a landing site, heating it enough to drive the trapped water vapor back out of the glass structure and capture it directly. The moon, in effect, has been quietly manufacturing and storing its own water supply for billions of years, using nothing more than sunlight-driven particle bombardment and ordinary silicate dust, long before anyone was around to make use of it. While the glass beads represented a mechanism for extracting water through processing, the next major discovery pointed to something more startling: a mineral where the water already exists in a stable, ready-made crystalline form. In 2024, researchers isolated a previously unknown mineral from the same batch of returned samples and confirmed it contained molecular water locked directly into its structure. They designated it an unnamed lunar mineral, and its discovery mattered enormously, because it marked the first time anyone had identified a hydrated mineral in samples collected from the moon's mid-latitudes, far from the permanently shadowed polar regions where water-bearing material was assumed to be confined. It helps to understand the distinction between this mineral and the glass beads discussed a moment ago. The glass beads contain hydroxyl, a single hydrogen atom bonded to a single oxygen atom, essentially a precursor form of water chemistry. This new mineral is different. It is a fully hydrated salt crystal, chemically identified as an ammonium magnesium chloride hexahydrate. The word hexahydrate is the important part. It means that for every unit of this mineral's crystal structure, 6 complete water molecules are locked permanently into the lattice. Water accounts for as much as 41% of the total mass of the crystal. If you happened to find a rock like this on Earth, it would look unremarkable. The kind of mineral that forms near certain volcanic vents, finding it on the Moon. In a region exposed to direct sunlight for 2 weeks at a stretch, was the surprising part. The landing site where this material was collected sits in a broad volcanic plain that experiences extended periods of direct solar exposure, with surface temperatures during the lunar day climbing high enough that, under the old assumptions, any surface water or ice should sublimate almost instantly and escape into space. That basic physics is precisely why researchers had long assumed sunlit regions of the Moon were essentially bone dry. Any water present at formation, they reasoned, would have evaporated away within a geological blink of an eye. The discovery of this hydrated crystal overturned that assumption. The water inside it survives the harsh thermal cycling of the lunar day, specifically because it is not sitting exposed on the surface. It is chemically bonded inside a salt lattice that behaves like a protective cage, shielding the water molecules from the conditions that would otherwise strip them away. This tells researchers something important. Water can persist in the Moon's mid-latitudes over geological timescales, provided it is incorporated into the right kind of mineral structure. The search for lunar water resources no longer needs to be confined exclusively to the cold, permanently shadowed floors of polar craters. There is an additional layer of significance to this particular mineral beyond the water it carries. Its chemical formula includes ammonium, which means it also carries nitrogen, an element that is essential for agriculture and for the production of certain rocket propellants, but one that is extremely scarce across the lunar surface as a whole. Finding a single mineral that contains both bound water and a nitrogen-bearing compound is, in practical terms, close to finding a natural, prepackaged survival resource. It hints that future lunar operations could process this material for drinking water on one hand, and for fertilizer or propellant chemistry on the other, turning what looks like an ordinary rock into a genuinely multi-purpose resource. The existence of this mineral also tells a geological story about the Moon's past. Its formation implies that volcanic gas releases at some point in lunar history were rich in exactly these volatile elements, water and nitrogen compounds among them, and that some of that material became trapped in mineral form before it could escape into space. That points toward a wetter, chemically richer volcanic history than the traditional dry moon model ever accounted for. The third major discovery moves away from water chemistry entirely and into the territory of advanced materials science, and it is arguably the strangest of the group. Graphene, when it comes up in ordinary conversation, is almost always described as a laboratory material, something painstakingly synthesized under carefully controlled conditions here on Earth. It consists of a single layer of carbon atoms arranged in a hexagonal lattice, and it is prized for being roughly 200 times stronger than steel by weight, while also being highly electrically conductive, which is why it shows up constantly in discussions of next-generation batteries, sensors, and electronics. It is not something anyone expected to find lying loose in lunar dirt. Yet that is exactly what turned up in an analysis of the returned samples. Announced in 2024, researchers identified naturally formed fulier graphene structures along with graphite flakes distributed through the soil. To appreciate why this is so unexpected, it helps to revisit the leading theory of how the Moon formed in the first place. A Mars-sized object is believed to have collided with the early Earth, and the resulting debris cloud eventually coalesced into the moon. That collision would have generated enormous heat. Heat intense enough that most volatile elements, carbon included, should have been boiled away and lost to space almost entirely. Under this model, the moon is expected to be a carbon-poor world. And for decades, the available data supported exactly that: abundant silicon and oxygen, but only trace amounts of carbon. The presence of organized graphene structures directly challenges that picture. Researchers used a non-destructive analytical method called Raman spectroscopy, which identifies a material's molecular fingerprint without damaging the sample, and confirmed that the carbon in the soil was not simply random soot or contamination. It was organized into the specific, high-quality crystalline arrangement that defines graphene. That kind of ordered structure does not happen by accident. It requires particular conditions. Sustained heat combined with a catalytic process that forces carbon atoms into that precise hexagonal geometry. The explanation researchers proposed is that this graphene was not delivered by meteorite impacts, as some carbon-bearing material on airless bodies can be, but was formed locally through a process referred to as an autochthonous origin, meaning it originated in place rather than arriving from elsewhere. The proposed mechanism connects to processes discussed earlier in this account: volcanic activity and solar wind bombardment. During the moon's periods of active volcanism, gas eruptions would have released carbon-bearing compounds onto the surface. At the same time, the surface was already being steadily bombarded by solar wind particles, including iron and protons. The theory holds that iron present in the soil acted as a catalyst, facilitating a chemical reaction that converted volcanic carbon gases into solid graphite and, in some cases, graphene. This finding forces a real update to how scientists think about the moon's chemical inventory as a whole. It suggests there was a native carbon cycle operating on the lunar surface that had gone entirely undetected until fresh, geologically diverse samples became available. There are practical implications here too. Carbon is fundamental to organic chemistry, and by extension, to any future effort to sustain agriculture or manufacturing on the moon. If there are genuinely harvestable carbon deposits present in the form of graphite or graphene, that solves a serious logistical problem for any long-term lunar settlement, because it means carbon would not need to be shipped in its entirety from Earth. It could, in principle, be sourced locally. It also reinforces a broader theme running through all of these discoveries. The moon's geological and chemical history appears to be considerably more complex and more dynamic than the relatively simple dry rock models of the 20th century assumed. Among the same batch of returned material, researchers also identified an entirely new lunar mineral, a microscopic phosphate crystal smaller than a human hair, which they named after the mission that collected it. What makes this particular mineral notable is that it contains trace inclusions of helium, an isotope implanted into its structure over billions of years of continuous solar wind exposure. Helium-3 is exceptionally rare on Earth, largely because our planet's atmosphere and magnetic field prevent solar wind particles from accumulating in surface materials the way they can on an airless, unshielded world like the moon. The isotope draws particular interest because of its potential role in advanced nuclear fusion research. Fusion reactions that use helium-3, sometimes discussed under the general category of aneutronic fusion, are theorized to produce usable energy while generating far fewer high-energy neutrons and far less associated radioactive byproduct compared to conventional deuterium-tritium fusion. which is the approach most current fusion reactor designs rely on. It is important to be clear that this remains a largely theoretical and still distant application. No fusion reactor capable of efficiently using helium-3 at meaningful scale currently exists, and building one remains a significant, unsolved engineering challenge. Even so, confirming that helium-3 exists in meaningful, naturally concentrated form within an actual lunar mineral strengthens the long-term case for the Moon as a potential future energy resource. Alongside the water-bearing materials and native carbon compounds already discussed, taken individually, these four findings, the hydrogen-charged glass beads, the hydrated mineral carrying both water and nitrogen, the naturally formed graphene, and the helium-3 bearing phosphate crystal, might each read as an interesting but isolated scientific curiosity. Considered together, though, they begin to look less like a random assortment of discoveries and more like a coordinated inventory of exactly the kinds of resources any long-term lunar operation would need: water for life support, nitrogen for agriculture, carbon for materials and chemistry, and a potential long-range energy source. That pattern becomes even more apparent once you factor in where the most recent of these samples actually came from. Which brings the story to a mission that represented a substantial leap in complexity over everything that preceded it. Every sample discussed so far, in fact every single gram of lunar material ever returned to Earth before this point, came from the near side of the Moon that includes all 6 crewed Apollo landings, the 3 robotic Soviet lunar sample returns, and the mission that had just supplied the water, mineral, graphene, and helium-3 discoveries covered above. 10 separate collection sites, and every one of them on the hemisphere that permanently faces our planet. Not a single physical sample had ever come from the far side, the hemisphere we never see from the ground. The reason for this is not a lack of ambition. It comes down to straightforward orbital mechanics. The Moon is tidally locked to Earth, meaning its rotation period exactly matches the time it takes to complete one orbit around our planet. The practical consequence is that the same hemisphere always faces us, while the opposite hemisphere never does. Any spacecraft operating on the far side loses direct line-of-sight radio contact with Earth the instant it passes beyond the lunar horizon, because the solid rock of the Moon itself blocks any signal trying to travel a direct path. You cannot command a rover, receive its data, or trigger a precisely timed launch sequence for a return vehicle if you have no way to communicate with it. For most of the space age, this communication barrier made a far-side sample return mission seem, if not strictly impossible, at least prohibitively difficult to justify against the cost. The relay satellite infrastructure, mentioned earlier in this account, first put in place to support the Farside rover landing, is what finally made a Farside sample return achievable. A dedicated relay spacecraft was placed in a specialized halo orbit positioned so it could maintain a clear line of sight to both a Farside lander and to ground stations back on Earth simultaneously, functioning as a communications bridge across the otherwise impassable barrier of the Moon itself. With that link firmly established, the mission that would ultimately deliver the Farside samples targeted one of the most striking geological features anywhere in the solar system, the South Palaitkin Basin. This is not an ordinary crater. It ranks among the largest and oldest impact structures known anywhere, stretching across roughly 2,500 kilometers and reaching extraordinary depths. The impact that carved it out billions of years ago was violent enough that many researchers believe it punched entirely through the Moon's crust and exposed material from the mantle underneath. That makes the region an unusually valuable target for sample collection, because it potentially offers direct access to material from deep inside the moon that simply is not available anywhere. On the near side, this basin also sits at the center of one of the moon's oldest unresolved mysteries, sometimes called the lunar dichotomy. Anyone who has looked up at a full moon has seen the dark patches that form the familiar face-like pattern, vast plains of ancient cooled lava known as Maria. Those dark plains dominate the near side. The far side, by contrast, is almost entirely free of them. Instead, it is covered in rugged highland terrain and a far denser concentration of craters, with a noticeably thicker crust overall. Why the two hemispheres of the same world ended up looking so fundamentally different has never been fully explained, and landing directly inside the South Pole-Aitken Basin gave researchers their best opportunity yet to gather physical evidence that might finally address it. The mission itself executed with remarkable precision. The lander touched down inside the Apollo crater, a smaller feature nested within the larger basin, and had only a short operational window, roughly 2 days, to collect both surface material using a robotic scoop and subsurface material using a drill. It then launched a small ascent vehicle directly from the lunar surface, which had to rendezvous and dock autonomously with an orbiting spacecraft. All of it coordinated entirely through the relay satellite rather than any direct communication path to Earth. Autonomous docking is a demanding maneuver, even with a direct communications line. Doing it exclusively through a relay bridge, for the first time in the history of sample return missions, added a layer of operational risk that no previous mission had ever had to manage. When the return capsule eventually touched down in Inner Mongolia, it was carrying just under 2 kilograms of material, and for the first time in human history, that material had come from the far side of the moon. Once those samples reached laboratories, the most pressing question researchers wanted to answer was not primarily about composition, but about timing. Geologists determined the age of volcanic rock using radiometric dating, a technique that measures the ratio of a radioactive parent isotope, commonly forms of uranium or related elements, to the stable daughter isotopes it decays into over time. Because these decay rates are extremely well understood and essentially constant, this ratio functions like an exceptionally precise natural clock, allowing researchers to calculate, often with a high degree of confidence, how long ago a given sample of rock solidified from molten lava. When this method was applied to basalt fragments collected from the far side, the results did not fit the existing narrative at all. The analysis indicated that volcanic eruptions were occurring on the far side of the moon as recently as roughly 2.8 billion years ago. To someone without a background in planetary geology, that might still sound impossibly ancient, and in an absolute sense, it is. But relative to what scientists had long assumed about the moon's thermal history, it is startlingly young. For decades, the standard model held that the moon, being a relatively small planetary body, would have lost its internal heat far more quickly than a larger world like Earth. Smaller bodies have a higher surface area to volume ratio, which means they radiate accumulated internal heat away more efficiently under this model. The bulk of lunar volcanic activity was expected to have peaked somewhere between 3.5 and 4 billion years ago, tapering off relatively quickly after that as the interior progressively solidified. This picture had already been complicated once before by the near-side samples discussed earlier, which showed evidence of volcanic activity as recently as roughly 2 billion years ago. itself far younger than expected. But researchers had a reasonably convincing explanation available for that particular result. The specific near-side region those samples came from happens to overlap with a geochemically distinct zone enriched in potassium, rare earth elements, and phosphorus, several of which include radioactive isotopes that generate heat as they decay. It was plausible to argue that this localized concentration of heat-producing elements acted like a built-in radiogenic heater, keeping that specific patch of mantle warmer and therefore volcanically active for longer than the rest of the moon. The far side offers no equivalent excuse. It lacks that same concentration of heat-generating elements. On top of that, its crust is measurably thicker than the crust on the near side. In some regions by dozens of kilometers, that thickness matters enormously for volcanism, because eruption requires two things simultaneously: magma hot enough to remain liquid, and sufficient pressure to force that magma up through the overlying crust to the surface. A substantially thicker crust behaves like a heavier lid pressed down over the mantle, actively suppressing eruptions even where liquid magma may still exist below. Given all of that, researchers expected the far side to have gone volcanically silent well before the near side did, lacking both the extra radiogenic heat source and the thinner crustal lid that made continued eruption easier. The 2.8 billion year date returned from the far side samples proves that is not what happened. Volcanic activity persisted there for roughly 1 billion years longer than the standard thermal models predicted, without the benefit of either advantage available to the near side. That single result forces a genuine reassessment of the moon's internal history. It suggests some additional mechanism, likely involving convection or periodic overturning within the lunar mantle, was redistributing heat more effectively than previously assumed, keeping the interior active and capable of producing magma across a much larger portion of lunar history than earlier models allowed, rather than a small world that cooled quickly and shut down early. The moon increasingly looks like a body with a more resilient, longer-lived internal engine, one that managed to sustain volcanic activity even in its most thermally disadvantaged terrain, long after conventional models expected it to have gone quiet. Viewed in isolation, each of these results reads as a fascinating but self-contained discovery. Water trapped in glass beads, a hydrated mineral carrying both water and nitrogen, naturally formed graphene, a helium-3 bearing phosphate crystal, volcanic rock from the far side that is far younger than it should be. Step back, though, and look at the entire lunar exploration program as a single, cohesive strategy rather than a series of disconnected missions, and these findings stop looking like isolated chapters in a geology textbook. They start looking like a deliberate resource survey. The stated long-term objective behind this entire body of work is the construction of a permanent lunar research station, a facility proposed jointly and since opened to broader international participation, intended to support sustained human and robotic activity on the surface rather than short-duration visits. Every discovery discussed so far functions as a direct input into whether that kind of long-term facility is actually feasible. You cannot build a sustainable, permanently staffed base if every liter of water, every gram of usable carbon, and every unit of propellant has to be launched from Earth. The cost of that kind of continuous resupply, at the volumes required to support a real settlement rather than a brief expedition, is simply too high to make the concept viable over any meaningful timescale. What is required instead is a genuine capacity for insights or resource utilization, the ability to extract and process what is already present on the moon, rather than shipping everything needed from Earth, considered through that lens. The hydrogen-charged glass beads and the hydrated mineral both point toward practical solutions for life support and potentially for propellant chemistry. The helium-3 findings point toward a longer horizon energy resource, contingent on fusion technology that does not yet exist but that continues to be actively researched. The naturally occurring graphene and graphite point toward a locally sourced material for construction and possibly for advanced electronics manufacturing, and the successful execution of a fully autonomous far-side sample return, coordinated entirely through relay infrastructure, demonstrates that the underlying logistics network, the communications architecture, the autonomous docking capability, the return vehicle design, is robust enough to support operations essentially anywhere on the lunar surface, not just in the more accessible nearside regions previously explored. Put together, this reads less like a purely scientific exploration campaign and more like the early resource mapping phase of an actual construction project, one that happens to be taking place on another world. The next stage of the program appears designed specifically to build on that groundwork rather than simply continue general purpose scientific surveying. 2. Further missions are already planned to carry this forward. The next mission in the sequence is targeted at the lunar South Pole specifically, with a primary objective of characterizing the substantial water ice deposits believed to be hidden inside permanently shadowed polar craters, regions so cold that any ice trapped there has likely persisted, undisturbed, for billions of years. Where earlier missions focused on chemistry and mineralogy across a range of terrain types, this mission is intended to map out the most viable location for a future permanent outpost. Ideally, a site that combines nearby access to shadowed ice deposits with terrain that also receives enough consistent sunlight to support solar power generation, a combination that is surprisingly difficult to find at the lunar poles given the dramatic low-angle lighting conditions there. Following that, another mission is planned that shifts focus away from pure exploration and toward direct technology demonstration. Rather than functioning primarily as a surveyor, this mission is intended to test whether lunar regolith itself can be used as a raw construction material, potentially through a process resembling three-dimensional printing, melting and reshaping local soil directly into structural components on site. If that concept can be validated even at a small scale, it would represent a critical proof point for the entire long-term vision of a lunar base built substantially from local material rather than components shipped in their entirety from Earth. Stepping back from the mission details, what all of this adds up to is a genuine shift in how planetary scientists are being forced to think about the moon. For most of the space age, the moon was treated primarily as a kind of time capsule, a body whose geological activity effectively ended billions of years ago, preserved since then in a more or less unchanging state, valuable mainly as a record of the early solar system rather than as a place with an ongoing story of its own. That framing made sense given the evidence available at the time. It just turns out to have been built on an incomplete sample. The picture emerging now is considerably more dynamic. This is a body with evidence of chemically active surface processes still running today, driven by ordinary sunlight and solar wind interacting with common minerals. It carries exotic, unexpected carbon chemistry that appears to be locally produced rather than externally delivered. It holds a plausible, if still distant, energy resource embedded directly in its soil. and its volcanic history extended roughly 1 billion years longer than standard thermal models predicted, even in the region least favorable to sustained volcanism. None of this describes a static, fossilized world. It describes a body that remained geologically and chemically active for a much larger fraction of its history than anyone assumed as recently as a decade ago. It is worth pausing on how unusual it is, scientifically speaking, for a body long treated as fully understood to be this thoroughly revised within the space of just a few years. Planetary science does not typically move this quickly. Most established models persist for decades precisely because gathering new physical evidence, especially sample return grade evidence from another world, is slow, expensive, and technically difficult. The speed of revision here is a direct consequence of a deliberate, patient engineering strategy. Build the mapping capability first, prove the landing and roving technology second, and only then attempt sample return at multiple sites, including one that had never been reached before. Once the fresh material was actually in the hands of geochemists working with modern laboratory instruments, the outdated models did not survive long. It is worth taking a step back to look more closely at how radiometric dating actually works, because this single technique is what allows scientists to make such a specific and confident claim as 2.8 billion years ago rather than a vague estimate like very old. The method relies on the fact that certain elements are radioactive, meaning their atomic nuclei are unstable and decay over time into different, stable elements at a rate that is fixed and does not change regardless of temperature, pressure, or chemical environment. Uranium, for instance, decays into lead through a long chain of intermediate steps, and the rate of that decay is described by a property called a half, the amount of time it takes for half of a given quantity of the radioactive element to convert into its decayed product. When molten rock cools and solidifies into a crystal, any radioactive uranium atoms present become locked into that crystal structure, along with essentially none of the lead they will eventually decay into. Since lead and uranium behave differently during the crystallization process and do not mix into the crystal at the same ratio, from that moment forward, the clock effectively starts. Uranium atoms trapped in the crystal steadily decay into lead atoms, and because both elements remain locked inside that same crystal structure, the ratio between them changes in a completely predictable way over time by measuring that ratio today. Using a mass spectrometer capable of counting individual atoms with extraordinary precision, scientists can calculate, working backward from the known decay rate, how long ago that crystal originally solidified from lava. This is why sample return missions matter so much, and why remote sensing from orbit, however detailed, can never fully substitute for physical material. An orbital instrument can identify a mineral's general chemical signature from a distance, and can sometimes make educated inferences about relative ages by counting the density of impact craters on a given surface. Since older surfaces accumulate more impact scars over time, but cratering statistics are an indirect, comparative measure, radiometric dating, applied directly to an actual rock sample in a laboratory, provides an absolute age with a level of precision and confidence that no remote technique can match. That precision is exactly why the 2.8 billion year date from the far side samples carries so much scientific weight. It is not an estimate derived from counting craters and extrapolating. It is a direct physical measurement of when that specific piece of rock crystallized from molten lava, the tidal locking that made the far side so difficult to reach in the first place is itself a fascinating piece of physics. And it did not happen by accident or coincidence. It is the long-term result of gravitational interaction between Earth and the Moon, playing out continuously over billions of years early in the Moon's history. It likely rotated at a different rate than it orbited Earth, meaning different parts of its surface would have faced Earth at different times, much like Earth itself rotates relative to the Moon today. But the Moon is not a perfectly rigid, perfectly symmetrical sphere. Earth's gravity exerts a slightly stronger pull on the near side of the Moon than on the far side, simply because the near side is closer, and this difference creates a subtle tidal bulge, a slight elongation of the Moon's shape along the axis pointing toward Earth, as long as the Moon's rotation and orbital period did not match. That tidal bulge would have continuously shifted position relative to the Moon's own surface as it rotated, and each shift would have generated internal friction, converting a small amount of rotational energy into heat and gradually slowing the Moon's spin. This process, called tidal locking, continued over an enormous span of time until the Moon's rotation period exactly matched its orbital period, at which point the tidal bulge became fixed in place relative to the surface, always pointing directly at Earth, and the gradual slowing stopped. From that point forward, the same hemisphere has always faced Earth, and the opposite hemisphere has never been visible from the ground, a state of affairs that has persisted for a large portion of the Moon's history and explains why an entire hemisphere of our nearest neighbor remained completely unsampled until relatively recently. This same tidal mechanism, worth noting, is still slowly at work today, though acting more on Earth than on the Moon at this stage. Tidal friction generated by the Moon's gravity acting on Earth's oceans is gradually transferring angular momentum from Earth's rotation into the Moon's orbit, which is why the Moon is very slowly moving away from Earth by a small fraction of an inch each year, and why the length of an Earth day has been gradually increasing over geological time. It is a genuinely elegant piece of orbital mechanics, one where the same fundamental physics explains both why the Moon shows us only one face and why Earth's own rotation continues to slowly change over deep time. The solar-wind interactions responsible for the water trapped in glass beads and for the helium embedded in lunar minerals deserve a closer look as well, because the underlying physics connects to something much larger than lunar geology alone. The Sun is constantly shedding material into space in the form of a continuous outward stream of charged particles, overwhelmingly protons and electrons, along with smaller quantities of heavier ions, including helium. This stream travels outward through the solar system at speeds typically in the range of several hundred kilometers per second, and it interacts differently with every object it encounters, depending heavily on whether that object has a strong magnetic field, a thick atmosphere, both, or neither. Earth has both. Our planet's magnetic field, generated by convective motion in its molten iron outer core, deflects the vast majority of incoming solar wind particles around the planet entirely, channeling only a small fraction down toward the poles, where the resulting interactions with the upper atmosphere produce the auroras. The atmosphere itself provides an additional layer of protection for anything that does get through. The Moon has essentially neither. It generates no significant global magnetic field of its own today, and its atmosphere is so thin that it barely qualifies as one at all, more accurately described as a collection of particles so sparse they rarely collide with one another. The result is that the lunar surface receives the solar wind essentially unfiltered, particle after particle, for billions of years, embedding itself directly into surface minerals through the same ion implantation process responsible for both the hydrogen trapped in glass beads and the helium-3 trapped in the newly identified phosphate mineral. This is not a purely academic point. It is the direct reason lunar regolith has become such a focus of interest for anyone thinking seriously about helium-3 as a future fusion fuel on Earth. Helium-3 is scarce, specifically because our atmosphere and magnetic field prevent this same solar wind implantation process from ever happening at meaningful scale. What little helium-3 exists on Earth comes primarily from the radioactive decay of tritium, a process used to produce only tiny quantities, nowhere near what would be required to supply a fusion economy. The Moon, lacking any equivalent shielding, has been quietly accumulating helium-3 in its surface soil for billions of years, in concentrations that, while still relatively dilute per ton of regolith, exist at a scale simply unmatched anywhere. On Earth, it is worth being precise about what helium-3 fusion would actually offer, since the concept sometimes gets discussed in slightly exaggerated terms. Most current fusion research, including the large international experimental reactors under construction today, relies on fusing deuterium and tritium to isotopes of hydrogen, because that reaction requires the lowest temperature and pressure to achieve compared to other fusion pathways, making it the most technically achievable option with current materials and engineering. The trade-off is that this reaction produces a large flux of high-energy neutrons as a byproduct. Those neutrons carry away a significant portion of the reaction's energy, and because they are electrically neutral, they cannot be directly captured or converted into electricity the way charged particles can. They simply escape and have to be intercepted with thick shielding, converting heat into steam over time. That neutron bombardment also gradually damages and activates the reactor's structural materials, creating a manageable but real radioactive waste stream. A reaction combining deuterium with helium, by contrast, is described as aneutronic, or nearly so, because the byproducts are primarily charged particles, energetic protons and helium nuclei rather than neutrons. Charged particles can, in principle, be captured directly and converted into electricity through electromagnetic methods, without needing to first convert their energy into heat and steam. And they do not carry the same neutron activation problem for the surrounding reactor structure. This is the theoretical appeal: potentially cleaner, more direct energy conversion with a smaller radioactive waste footprint. The catch is that a deuterium-helium-3 reaction requires substantially higher temperatures and pressures to sustain than deuterium-tritium fusion does, which is precisely why no research program has yet built a reactor capable of doing this efficiently at any meaningful scale. It remains, for now, a promising theoretical pathway rather than a near-term engineering reality. And any serious lunar helium-3 mining program would only become economically justified once, or if that reactor technology matures on Earth. The discoveries described here do not change that timeline. What they do is confirm, with direct sample evidence rather than orbital inference, that the raw material genuinely exists on the Moon in a naturally concentrated mineral form, which matters for long-range planning, even if the fusion technology needed to use it is still some distance away. Turning back to the carbon story, it is worth unpacking the giant impact hypothesis a little further. since it is the backbone of why a carbon-poor moon was ever the expected outcome in the first place. The model proposes that in the early solar system, a planetary body roughly the size of Mars, sometimes referred to informally as they, collided with the still-forming Earth at a glancing angle. The impact would have been almost unimaginably energetic, vaporizing a substantial portion of both bodies and throwing a vast cloud of superheated debris into orbit around Earth. Over a relatively short period of time, on the order of a few decades to perhaps a couple of centuries by some estimates, that debris cloud cooled and gravitationally coalesced into the moon. Because this formation process involved such extreme temperatures, models predict that many volatile elements and compounds, substances with relatively low boiling points, would have simply boiled off into space rather than being retained in the newly forming moon. Carbon compounds, along with water and various other volatiles, fall squarely into this category. This is the theoretical basis for describing the moon as inherently volatile depleted compared to Earth, and it is a big part of why the Apollo and lunar samples, when analyzed decades ago, showed such limited carbon content. The theory fit the available evidence well for a long time. The graphene and graphite discoveries do not overturn the giant impact hypothesis itself, which remains well supported by other independent lines of evidence, including the striking chemical similarity between lunar and terrestrial rock in several other respects. What they do challenge is the assumption that the moon has remained carbon-poor across its entire subsequent history. If volcanic outgassing later in lunar history released carbon-bearing compounds onto the surface, and solar wind exposure combined with catalytic iron in the soil converted some of that carbon into ordered graphitic structures over time, then the moon's current carbon inventory would reflect billions of years of ongoing surface chemistry layered on top of an initially carbon-poor starting point, rather than reflecting that initial depletion alone. In other words, the moon may have started out largely carbon-poor, exactly as the giant impact model predicts, and then slowly built up localized carbon-rich deposits afterward through entirely separate volcanic and space weathering processes. Both things can be true simultaneously, and reconciling them is now an active area of ongoing research. It is also worth putting some of graphene's practical properties in plainer terms, since the material comes up frequently in modern technology discussions without always being clearly explained. A single sheet of graphene is only one atom thick, the thinnest possible arrangement of ordinary matter, yet it is exceptionally strong relative to its weight, largely because the carbon atoms are locked into a rigid hexagonal pattern with extremely strong chemical bonds between neighboring atoms. That same atomic arrangement also makes graphene an outstanding conductor of both electricity and heat, since electrons can move through the material with very little resistance. These properties are why graphene shows up so often in research aimed at next-generation batteries, flexible electronics, advanced sensors, and lightweight structural composites. Producing high-quality graphene reliably on Earth, however, remains a genuinely difficult and often expensive process, which is part of why finding naturally formed graphitic material on the moon, even in relatively modest quantities, is scientifically interesting well beyond its resource value alone. It raises questions about whether similar natural graphene forming processes might occur on other airless, volcanically active bodies throughout the solar system, places that have never been sampled closely enough to check. It is worth taking a moment to appreciate just how thin the original evidence base actually was. because it puts the scale of this recent revision into proper perspective. The Apollo program carried out 6 crewed landings between 1969 and 1972. And across those 6 missions, astronauts collected a combined total of a few hundred kilograms of lunar material. The Soviet Union's robotic lunar program added 3 additional, much smaller sample returns during roughly the same era, the largest of which brought back only about 170 grams. All of it, without exception, came from near-equatorial sites on the near side, chosen in large part because those locations were the safest and most operationally straightforward places to attempt a landing with the technology available at the time, not because they were considered the most geologically representative regions of the Moon as a whole. This was, by any reasonable standard, an extraordinary scientific achievement for its era, accomplished with computing power and guidance technology that looks primitive by modern standards. But it inevitably produced a narrow, geographically concentrated data set, and the broader models of lunar formation, composition, and thermal history that were subsequently built from it inherited that same narrowness. Whether or not anyone fully appreciated it as such at the time, for nearly 50 years afterward, essentially every textbook description of lunar geology rested on evidence gathered from a small handful of sites, clustered in one general region of one hemisphere. This helps explain why the recent findings feel less like an incremental update and more like a genuine overhaul. It is not that the earlier scientists were careless or that their analysis of the Apollo and lunar material was flawed. Their conclusions were generally sound. Given the sample they had access to, the issue was always the sample itself, its limited geographic scope, not the rigor applied to studying it. Once material from meaningfully different regions, a younger volcanic plain on the near side, and, for the first time ever, material from the far side, became available for analysis using instrumentation far more advanced than anything available in the 1970s. It was almost inevitable that at least some long-standing assumptions would need revision. The surprising part was less that revisions happened at all, and more just how substantial some of them turned out to be. The lunar dichotomy, the stark visual and geological difference between the heavily cratered, mare-poor far side and the mare-covered near side, remains one of the more stubborn, open questions in planetary science. And it is worth noting explicitly that the recent far-side samples have not fully resolved it, even though they have added valuable new data. Several competing explanations have been proposed over the years. One idea suggests that a colossal, glancing secondary impact early in lunar history disproportionately affected one hemisphere, contributing to the crustal thickness difference observed today. Another proposes that the concentration of heat-producing radioactive elements on the near side, the same geochemically distinct region mentioned earlier in connection with the near-side volcanic activity, created an asymmetric internal heating pattern that in turn produced asymmetric volcanic resurfacing. A third line of thinking points toward differences in the timing and thickness of the Moon's early magma ocean solidification between the two hemispheres, potentially influenced by Earth's own gravitational and thermal proximity during that formative period, since one hemisphere always faced a much closer, much hotter early Earth than the other did. None of these explanations is universally accepted, and it is entirely possible that more than one mechanism contributed simultaneously rather than there being a single, clean cause. What the far-side samples do provide is a genuine physical anchor for testing these competing ideas going forward, since researchers finally have actual dated rock, and not just remote, spectral, and topographic data, from the very terrain the dichotomy question is centered on. future analysis of additional far-side material, potentially including samples from future missions targeting different sites within or near the same basin, will likely be needed before this particular question moves from an open debate to a settled conclusion. It is also worth situating these lunar findings within the broader landscape of planetary geology, because the Moon is far from the only body in the solar system whose geological activity has turned out to be more persistent than early models assumed. Mercury, a planet close enough to the Sun that it might seem an unlikely candidate for prolonged internal activity, has shown orbital and surface evidence suggesting some degree of ongoing internal contraction and possible low-level tectonic activity far more recently than older models predicted. Mars, long treated as a similarly cold and geologically inactive world, has produced seismic data from surface instruments indicating that likely driven by residual internal heat and ongoing tectonic stress continue to occur today, and some of the planet's largest volcanic structures may have experienced eruptions within the last few million years. A blink of an eye in geological terms. Jupiter's moon, Io, by contrast, represents the opposite extreme entirely. A body kept intensely volcanically active, not by leftover formation heat, but by continuous tidal flexing generated through its gravitational relationship with Jupiter and neighboring moons, making it the most volcanically active body known anywhere in the solar system. Taken together, these examples point toward a broader pattern that planetary scientists have been increasingly forced to accept over the past couple of decades. Small or seemingly cold planetary bodies are, on the whole, considerably more likely to retain some degree of ongoing internal activity, whether volcanic, tectonic, or otherwise, than the simplified thermal cooling models of the 20th century assumed. The Moon's extended volcanic history, now anchored by direct sample evidence from both hemispheres, fits neatly into that broader trend rather than standing apart from it as some kind of isolated exception. It suggests that the tools and assumptions planetary scientists use to model the interior evolution of small, rocky, and icy bodies throughout the solar system, and by extension, similar bodies orbiting other stars, likely need broader revision, not just in the specific case of Earth's own moon. The proposed lunar research station itself deserves a closer look, since it is the practical endpoint that gives all of these individual discoveries their shared context. Originally announced as a joint effort between China and Russia, the project has since drawn interest and stated participation from a broader group of countries and research institutions, reflecting a growing recognition that a permanent lunar outpost is likely to be an international undertaking by necessity, given the scale of infrastructure involved. Current planning envisions the effort unfolding in phases across the coming decade and beyond, starting with robotic reconnaissance and resource verification missions of the kind already discussed, before moving toward the delivery of surface infrastructure capable of supporting longer duration robotic operations, and eventually, further into the future, sustained human presence. This phased approach mirrors, in a broader sense, the same orbit, land, and return logic that defined the earlier sample collection missions, before committing to permanent human infrastructure. Mission planners want confidence that the necessary resources genuinely exist in usable, extractable quantities at the chosen site, that the technology required to process those resources into water, oxygen, propellant, or construction material actually works reliably under real lunar conditions, and that a sufficiently robust communications and logistics network can support continuous operations rather than brief, isolated missions, each of the discoveries covered throughout this account maps directly onto one of those requirements, which is part of why they have generated as much interest within the space engineering community as they have within pure planetary science circles. It is worth being appropriately cautious here as well. None of these discoveries mean that building a functioning lunar base is now simply a matter of engineering execution with all major scientific unknowns resolved. Confirming that a resource exists in a sample returned from one specific site is a meaningful first step, but it is a long way from confirming that the same resource exists in extractable concentrations across a broad enough area to support continuous operations, or that the processing technology required to extract it can be miniaturized, made reliable, and made efficient enough to operate unattended for years at a time in an extremely harsh environment. The glass bead water estimate, for instance, the figure describing a potential 270 billion tons of water distributed globally across the upper regolith layer, is an extrapolation based on the concentration measured in one particular sample set, not a direct global survey. Extrapolations of this kind are scientifically reasonable and useful for planning purposes, but they carry real uncertainty, and future missions specifically designed to test that estimate across other locations will be an important part of confirming just how reliable it actually is. This is precisely the kind of question the next planned mission, focused on the lunar South Pole and its permanently shadowed craters, is intended to help answer if genuinely large, easily accessible water ice deposits are confirmed to exist there. That would represent an even more concentrated resource than the diffuse hydrogen trapped within glass beads across the wider regolith, and it would likely shape exactly where any future permanent base ends up being built. The interplay between these two very different potential water sources, diffuse but geographically widespread hydrogen trapped in ordinary sunlit soil, versus concentrated but geographically confined ice hidden in permanent polar shadow, is likely to be one of the more important open questions driving lunar resource strategy over the next decade. There is also a broader scientific dimension to all of this that extends well beyond questions of lunar habitability or resource extraction. Everything learned here about how airless bodies interact with solar wind, how impact glass forms and behaves chemically over geological time, how volcanic activity can persist far longer than simple thermal models predict, and how hydrated minerals can remain stable even in seemingly hostile surface conditions, feeds directly into how scientists model surface conditions and long-term evolution on other airless or thin atmosphere bodies throughout the solar system, and increasingly on rocky planets and moons being studied around other stars entirely. This matters more than it might initially seem to, because direct sample analysis of exoplanets is not remotely possible with current or foreseeable technology. Everything astronomers currently know about the surface composition and geological history of planets orbiting distant stars comes from indirect methods, analyzing starlight that passes through or reflects off a planet's atmosphere, measuring subtle changes in a star's own light as a planet transits in front of it, or, in a small number of cases, directly imaging extremely faint light reflected from the planet itself. None of these methods can currently resolve the kind of fine-grained mineralogical or chemical detail that a physical sample provides. What they can do, though, is compare observed patterns against models built from bodies we actually can study directly, our own moon among them. A model of how solar wind bombardment builds up trapped volatiles in silicate glass over billions of years, refined and validated using actual lunar samples, becomes a genuinely useful reference point for interpreting more ambiguous, indirect signals detected around airless, rocky exoplanets many light-years away. In that sense, every one of these lunar discoveries functions simultaneously on two very different scales, as a piece of practical resource planning for a specific future human outpost roughly 400,000 kilometers from Earth, and as a calibration point for models scientists use to interpret worlds they may never be able to visit or sample directly at all. It is also worth acknowledging that this renewed wave of lunar sample science has not unfolded in isolation. Other national space programs have their own active lunar efforts underway, including crewed lunar landing programs and additional robotic sample return concepts targeting different regions of the Moon, particularly the polar areas where large ice deposits are suspected to exist. Taken as a whole, the current era of lunar exploration looks meaningfully different from the first one, where the original space race era was largely defined by a small number of crewed missions concentrated within a short span of years, followed by a long pause. The current period involves multiple overlapping robotic and eventually crewed programs, often targeting complementary rather than duplicate objectives, and increasingly built around the shared, practical goal of establishing some form of sustained lunar presence rather than a single symbolic landing. This shift matters for the pace of scientific discovery, specifically because more missions, targeting more distinct regions, using increasingly capable instrumentation, translates directly into a broader and more representative sample base for researchers to work with. The narrow, near-side-only sample record that shaped lunar science for nearly 50 years was never going to be corrected by theoretical work alone. It required new physical material from new places, and the current spread of international lunar activity, whatever the underlying motivations of any individual program, is collectively producing exactly that. Every additional sample return mission from a new region reduces the geographic bias that shaped the earlier consensus. Whether the specific new samples come from polar ice deposits, additional far-side sites, or previously unsampled near-side terrain, there remain a considerable number of open questions, even after everything covered so far. Chief among them is what mechanism, precisely, allowed the far side's mantle to remain active long enough to produce eruptions 2.8 billion years ago, given that it had neither the radiogenic heat advantage nor the thinner crust available to the near side. Researchers have proposed mantle convection or periodic overturning as a general category of explanation, but the specific dynamics involved, how heat moved, how magma accumulated enough pressure to breach a notably thick crust, and why this particular region rather than others sustained activity for so long, remain active areas of modeling and debate rather than settled conclusions. Additional samples from other far-side locations, ideally including sites outside the South Pole Lightcon Basin, would help determine whether this extended volcanic activity was a broadly distributed, far-side phenomenon or something more localized to this specific, unusually deep impact basin. Similarly, while the newly identified hydrated mineral demonstrates that water can survive in sunlit lunar terrain when properly shielded within a salt lattice, it remains an open question just how widespread this particular mineral or similar hydrated compounds might be across other volcanic plains on the Moon that have not yet been sampled directly. The glass bead water reservoir estimate faces a comparable uncertainty, since it is currently based on extrapolating from material collected at a limited number of sites rather than a comprehensive global survey, confirming or refining that estimate will likely require either additional sample return missions from a wider range of locations or sufficiently advanced remote sensing instruments capable of detecting these signatures more precisely from orbit, ideally cross-validated against physical samples, the way the current estimates already have been. The graphene and graphite findings raise their own open questions as well, particularly around how widespread this autochthonous carbon-forming process actually is across the lunar surface, and whether it might also be occurring, largely undetected so far, on other airless, volcanically active or formally active bodies throughout the solar system that have never had material returned from them for direct laboratory analysis. And the helium-3 findings, while scientifically confirmed as present in a natural lunar mineral, remain tied to a genuinely uncertain long-term timeline. Since large-scale helium-3 fusion depends on reactor technology that does not yet exist in any commercially viable form, and there is no way to confidently predict when, or even definitively whether, that technology will mature to the point where lunar helium-3 extraction becomes economically justified. It is easy, when moving quickly through a list of chemical and mineralogical discoveries, to lose sight of just how much dedicated engineering work sits underneath each one of them, and it is worth pausing to give that engineering its due. Every one of these findings depended on a chain of technology that had to work correctly, in sequence, across an environment with essentially zero room for error. A rocket had to launch successfully, a lander had to touch down intact on unfamiliar terrain, using either pre-mapped landing zones or autonomous hazard avoidance during final descent. A drill or robotic scoop had to collect material without damaging or contaminating it. A small ascent vehicle had to launch itself directly off the lunar surface, with no runway, no atmosphere to provide lift, and no room for a second attempt. That ascent vehicle then had to rendezvous and dock with an orbiting spacecraft entirely autonomously, a maneuver that is difficult even in Earth orbit with direct human oversight, and immeasurably harder around the Moon, especially when operating on the far side and relying entirely on a relay satellite. For every single command and every piece of telemetry, none of these steps are new in the sense that similar maneuvers were performed decades ago during the Apollo program. But it is worth remembering that Apollo benefited from direct human piloting for many of its most delicate maneuvers, with astronauts able to make real-time adjustments based on what they could see and feel. A fully robotic sample return mission has to encode all of that same judgment into pre-programmed logic and autonomous decision-making systems, executed by a spacecraft with no human aboard to intervene if something unexpected occurs, extending that same fully autonomous process to the far side of the Moon, where a communications delay through the relay satellite adds further complexity to any real-time troubleshooting, represents a genuine escalation in engineering difficulty, not a simple repeat of previously solved problems. This is worth emphasizing because it speaks to why this particular scientific transformation happened when it did, rather than decades earlier, the chemistry being discovered, the presence of hydrated minerals, native graphene, helium-3 bearing crystals, was always there, embedded in the lunar surface long before any spacecraft ever approached it. What changed was not the Moon. What changed was humanity's capacity to reach previously inaccessible regions of it, retrieve physical material, and bring it home intact for analysis using instruments sensitive enough to detect and characterize these materials at the atomic and molecular scale. Every discovery covered throughout this account is, in a very real sense, a joint product of chemistry that has been quietly happening on the lunar surface for billions of years. An engineering capability that has only existed for the past few years. There is also a useful lesson buried in this story about the difference between remote sensing and direct sampling. One that extends well beyond lunar science specifically. Orbital instruments are extraordinarily valuable. They can survey vast areas quickly at a fraction of the cost of a landed mission. And they are essential for deciding where a future sample return mission should even target. But they fundamentally measure things indirectly, inferring composition from reflected or emitted light across various wavelengths, or inferring subsurface structure from radar or gravity measurements. Those inferences are powerful, but they are still inferences, built on models of how certain materials are expected to behave. Models that can turn out to be wrong or incomplete in ways that are difficult to detect from orbit alone. A returned sample removes that layer of inference almost entirely. Researchers can place the material directly under an electron microscope, run it through a mass spectrometer, expose it to Raman spectroscopy, and measure its properties with a level of certainty simply unavailable from any distance. This is precisely why the 44-year gap in sample return mattered so much, and why closing it produced results significant enough to overturn assumptions that had persisted, essentially unchallenged, since the 1970s. Remote sensing had continued throughout that entire gap, adding useful detail year after year. But it could never fully substitute for physical material back in an actual laboratory. The moment that material became available again, several long-standing assumptions did not survive contact with it. Pulling all of this together, the moon that scientists describe today looks substantially different from the one described in textbooks even a decade ago. It is no longer treated as a geologically dead relic, frozen in place since shortly after its formation and useful mainly as a preserved record of the distant past. It now appears to be a body with an active, ongoing surface chemistry driven by sunlight and solar wind. A volcanic history that extended roughly 1 billion years longer than older thermal models allowed. A naturally occurring and only partially explained carbon inventory, and a resource profile, water, nitrogen-bearing compounds, structural carbon, and a rare fusion isotope that happens to align remarkably well with what any long-term human outpost would actually need. None of this makes the moon a place teeming with ongoing dramatic geological activity in the way of a restless world like Io is. Compared to Earth, or even to Mars, the moon remains a quiet, slow-moving body by almost any measure, but quiet is not the same thing as inactive. And the distinction between the two turns out to matter enormously, both for basic planetary science and for very practical questions about future habitation. A world that stopped evolving billions of years ago and a world that has continued evolving slowly, in ways too subtle to detect without direct sampling, are fundamentally different objects to study, and until very recently, there was no way to definitively tell which kind of body the moon actually was. That distinction is now considerably clearer, though not entirely settled. The mechanism sustaining far-side volcanism for so long without the near-side's radiogenic heat advantage remains incompletely understood. The true global extent of the water-bearing glass beads and the newly identified hydrated mineral remains an extrapolation awaiting further confirmation from additional sites. The full scope of the moon's native carbon-forming chemistry, and whether similar processes occur on other airless bodies throughout the solar system, remains an open and active research question, and the practical timeline for any of this translating into a genuine, functioning lunar resource economy depends on engineering milestones, particularly around fusion technology and large-scale in situ resource processing that have not yet been achieved anywhere, on the Moon or on Earth. What is different now, compared to even 5 years ago, is that these are no longer purely theoretical questions waiting on data that does not exist. They are specific, well-defined scientific problems, each one tied to a concrete follow-up mission already in some stage of planning. The upcoming South Pole mission is designed specifically to test the scale of polar ice deposits and help resolve exactly how they relate to the more diffuse water locked in sunlit regolith elsewhere. The planned regoliths processing demonstration mission is designed specifically to test whether in situ construction from local lunar material is actually achievable, rather than simply theoretically appealing. Future far-side missions, wherever they ultimately target, will help clarify whether the extended volcanic activity observed at the South Pole Basin was a broad far-side phenomenon or something more localized to that particular, unusually deep impact structure. This is, in many ways, what makes this particular moment in lunar science so genuinely interesting to follow, independent of any longer-term ambitions around habitation or resource extraction. It is rare for a body this well studied, this close to Earth, and this thoroughly picked over by earlier generations of scientists, to still be capable of producing findings that meaningfully overturn textbook assumptions. The Moon has been observed through telescopes for centuries, orbited by dozens of spacecraft, and walked on by 12 human beings. And yet, within the space of just a few years, a handful of well-targeted sample return missions have revealed water where none was expected, carbon chemistry that should not exist under the standard formation model, and volcanic activity that persisted far longer than any thermal model predicted. That is a genuinely unusual outcome for a body this extensively studied, and it says something important about the limits of remote observation compared to direct physical sampling. No matter how sophisticated our orbital instruments become, looking ahead, the most interesting open question may not be any single one of the specific chemical or geological puzzles described throughout this account, but rather a broader one. How many other assumptions about the Moon, built on that same narrow, near-side-only sample record from the 1960s and 70s, are still sitting unchallenged simply because nobody has yet returned the right sample from the right location to test them? Every mission described here targeted a specific, deliberately chosen region precisely because it looked different from anything sampled before. And every one of those missions came back with at least one genuine surprise. There is no obvious reason to assume that pattern will stop now that a handful of new sites have finally been sampled. If anything, the consistency of that pattern across 4 separate missions suggests the Moon still has a great deal left to reveal, provided researchers keep choosing new, previously unsampled terrain to investigate. That is ultimately the through line connecting everything discussed here, from the 44-year gap in sample return to the careful 3-phase engineering roadmap that eventually closed it, to the specific water, carbon, and mineral discoveries that followed, and finally to the ambitious plans now underway for a permanent lunar research station. Each piece depended on the one before it, and each new piece of evidence has, so far without exception, complicated the simple story that once described our nearest neighbor as a dry, dead, unchanging rock. The Moon turned out to be considerably more chemically active, more geologically persistent, and more resource-rich than the evidence available for most of the space age ever suggested, given how much was hiding in plain sight in soil that had simply never been properly examined until now. It is worth staying genuinely curious about what the next round of samples, from the poles, from additional far-side sites, from wherever the next mission ultimately targets, might still have left to reveal, following this story as it continues to unfold. Mission by mission and sample by sample is very much worth doing, because if the pattern of the last several years holds, the moon is nowhere near finished surprising the people studying it. It is worth returning briefly to that small cotton sprouting experiment mentioned earlier, because it is easy to treat it as a minor footnote when it actually captures something important about how these missions were designed. The experiment consisted of a small, sealed canister carrying cotton seeds along with a handful of other organisms, launched as a secondary payload on the mission that achieved the first ever soft landing on the far side. Inside that sealed environment, the seeds were kept at a stable temperature and supplied with water and nutrients. Isolated from the extreme temperature swings and airless conditions of the lunar surface outside the canister, photographs sent back showed a small cotton sprout, the first time any plant had ever germinated in a lunar environment, even one artificially maintained inside a protective container. The experiment did not last long. Without the ability to actively regulate temperature indefinitely, the canister could not protect its contents once the extended cold of the lunar night set in, and the sprout did not survive that transition. But the experiment was never intended to demonstrate long-term viability. It was a proof of concept, confirming that basic biological processes, germination in particular, could occur within a controlled environment on the lunar surface, a small but genuine building block toward the much larger, much later goal of sustaining biological systems, whether for research or eventually for food production, as part of any long-term lunar presence. It sits alongside the mineralogical and chemical discoveries covered throughout this account as another small piece of the same larger puzzle, figuring out what is actually required, biologically as well as chemically, to keep people alive and productive on the lunar surface for extended periods. It is also worth being honest about the uncertainty that surrounds several of the headline figures discussed throughout this account, since precise-sounding numbers can sometimes create a false impression of certainty. The estimate of roughly 270 billion tons of water, potentially held within the moon's upper regolith layer, is a genuinely useful figure for planning purposes. But it is derived by measuring the concentration of hydrogen-bearing glass beads in a limited number of return samples, and then extrapolating that concentration across the entire lunar surface, assuming a reasonably uniform distribution. Real distribution is very unlikely to be perfectly uniform. Some regions, particularly those with a longer or more complex history of volcanic glass formation, may hold meaningfully more than this average figure suggests, while other regions, especially those dominated by older, more heavily weathered highland material rather than younger volcanic plains, may hold considerably less. Similarly, the far side volcanic age of roughly 2.8 billion years applies specifically to the basalt fragments actually analyzed from the samples collected at that particular site within the South Palaitkan Basin. It does not necessarily mean that every part of the far side remained volcanically active until that same point in time. It is entirely possible that this specific location, perhaps because of some local variation in crustal thickness or mantle composition not yet fully understood, remained active longer than the far side average, or, alternatively, that this age is genuinely representative of far-side volcanism more broadly, and other still unsampled far-side regions would show similarly late activity if properly dated. Distinguishing between those two possibilities is exactly the kind of question that additional far-side sampling from meaningfully different locations within that hemisphere will eventually help answer. None of this uncertainty undermines the significance of what has been found so far. It simply reflects the ordinary, healthy skepticism that responsible planetary science applies to any new result, especially one derived from a still limited sample size relative to the size of the object being studied. Extraordinary findings drawn from a small number of samples are not final answers in themselves. They are strong, well-supported hypotheses that reshape the immediate research agenda, pointing directly toward the specific follow-up questions and follow-up missions needed to confirm, refine, or in some cases revise them further. That is precisely the position lunar science currently finds itself in. Several major, well-supported discoveries, each opening up a clear and specific set of next questions, with concrete missions already planned to help answer them. That is the version of the moon worth carrying forward. From here, not a settled subject, closed off decades ago by a handful of missions from the 20th century, but an active area of discovery with real samples in real laboratories still being analyzed, and real missions already scheduled to test the next round of questions this same body of work has opened up.